Hello everyone, my name is Devendra Kapadia and I'm the manager of calculus and algebra at Wolfram. Welcome to this presentation on the core calculus features in version 12 of the Wolfram language. So this presentation will be in two parts. In the first part, I'll give you a brief overview of the features page which you're seeing right now. And then in the second part, my colleague Itai Seggev, senior kernel developer at Wolfram, will give you a live demo of the new calculus functions and features in version 12. Now, when you think of calculus and the Wolfram language, this is something we've been good at ever since version 1. And you might wonder what was left to be done. But what we noticed in the last few years is that the number of people using calculus has really shot up, has increased. And in fact, students are learning calculus at an even younger age in high school and even earlier. And the reason for that is that this is now a modeling language par excellence. And if you apply for a course in data science or economics or engineering, the first thing you'd be asked is, how good are you at calculus? So it looks like calculus is at the peak of use and interest right now. And so we told ourselves, let's try and make this release a great one for calculus. So we had 4 objectives. The first one was to make calculus in the Wolfram language even more powerful by adding new functions and algorithms. We wanted to make contact with image processing and other applications. We wanted it to make it easier to use our calculus functions by giving more documentation. And last but not the least, we wanted to fulfill a desire to teach calculus itself using the Wolfram language. So all that's been achieved in version 12, and I'm really happy to note that we have a version in which it's much easier to learn calculus, to apply calculus using the Wolfram language. So let's begin with a brief list of things which have improved or are new. So we have new algorithms for function limits, support for undirected and multivariate limits, a new sequence limit functions, a standard feature in calculus courses. We can now calculate upper and lower limits. There are nth order derivatives, a big step from the ordinary derivatives from calculus. At long last, we can find constants of integration and summation. We have new integral transforms, the Hunkel and Radon transforms from image processing. We have a very large number of new indefinite integrals and special sums. DSolve continues to get improved version by version. So we looked at standard benchmarks, Mathematica Stack Exchange posts, etc., and said, how can we make DSolve even better? And we've done that for this version. There are more periodic integral transforms which have been computed, summation transforms, new support for using Weierstrass and elliptic functions, and for users at the lowest level, we have very nice new reference pages for college calculus functions like D, limit, and integrate. And for people who are more advanced, we have more than 4,000 new examples of mathematical functions and how to use them in the Wolfram language. So all in all, we have a very comprehensive set of features which makes calculus even more attractive to learn and use using the Wolfram language. So now let me give you a brief overview of the examples on the page, the way you can learn about the new features. So each row over here is like a section of a notebook. And in fact, they were sections of a notebook. So the first row over here talks about limits, function limits, and multivariate limits. The second row is about sequence limits, recursive sequence limits, other things. The third row is about nth derivatives and how you can apply them in practice. A very nice new feature. Here we talk about constant integration summation, the familiar C1 from calculus, new class of integral and sums, what we have made better in this version, the Hunkel and Radon transforms. So that's about all for the mathematical part, the core algorithms. And then beyond that, we have some new special functions like it's talked about. And then we have the new improved documentation for college calculus, the new special function documentation, and the Wolfram U calculus course, which has proved to be extremely popular. So this page gives you a pretty good idea of what's new in version 12 and how you can learn about it. Of course, there's a long list of functions that have changed, improved, etc. And that's over here. We have the new asymptotics guide page, which you might want to look at as well. We've been quite good at writing blog posts in this team. We wrote a blog post for version 11.1 for derivatives, then limits, Wolfram calculus. There's lots of stuff over here which you can learn the new features in much more detail. So let's now look a little more carefully at some of the examples on this page. So I'm going to talk about upper and lower limits of multivariate functions, which kind of brings all the new limit functionality together. So here is a bivariate function, two variables x and y. And the question is, what happens as you approach the origin in x and y? So the first point over here is, if you look at the plot over here, it's clear that there's no definite limit, but the function seems to kind of oscillate between two planes. And in fact, the new limit function, I tell you that the limit itself doesn't exist, but the lower limit is -1 over square root of 2, and the upper limit is 1 over square root of 2. So that's a very nice way of studying the limit behavior of a function near the origin. So on to sequence limits, and again, let's look at upper and lower limits. So here is a trig function sequence. It's clearly oscillating, but the lower limit is -3, as you can see over here. And if you want to find the upper limit for a slightly wilder sequence, this sequence has got sines and cosines. It's a pretty hard sequence to work with, but we can find the upper limit in this case using the new max limit functionality for discrete sequences. Now, of course, if you have a sequence that converges, then you have the limit, the max limit, and the min limit all being equal. And finally, if you know that the limit doesn't exist, you can still ask the question, why does it not exist? Well, in this particular case, which you see in front of you, you have the odd and even sequences, subsequences behaving a little differently, and hence you have no limit for this sequence. So that's function limits and sequence limits. Beyond that, we have nth derivatives. Now, when we began this project, it looked like this was kind of just a new advanced topic in calculus, but we soon realized that these nth derivatives are actually quite important in applications. So here's an example. You have a Gaussian function over here. You've got its nth derivative. That looks pretty daunting. You could have worked out the first or second derivative by a chain rule, but that's the nth derivative. But as soon as you put n equal to 5, you get back a nice familiar expression in terms of the Hermite polynomials. And in fact, some time ago, it was pointed out that these higher order derivatives, in fact, generate oscillations. So they are much like trigonometric functions. They have the same oscillatory behavior, and you can use them for all kinds of practical applications. And in fact, Gaussian filtering and image processing uses just the same idea to generate these plots. And hence you see that these nth derivatives, which look very kind of theoretical, are in fact quite useful in practice. Okay, on to integrals. Now, we always regard integrate as one of our prize functions in calculus, and the question is, what more could we do with it? Well, we tested around 80,000 examples with integrate and asked ourselves, what doesn't work right now? And we found around 1,100 of them. Then we tested more and said, okay, those ones over here are the only ones that we really want to improve because they work really well in the system. So that's a sample of the new integrals that work in version 12. They are all kind of a little exotic, but in fact, they do affect users from day to day. And on the other hand, we have lots of new sums that can be worked out in version 12. They come from Math World and other sources, but basically we have even more powerful integration and summation capabilities in this new version. So like I mentioned earlier on, we have the new Hunkel transforms, which basically are two-dimensional Fourier transforms. But to me, the crowning piece for integral transforms really are the so-called Radon transforms. So you see, around around a century ago, Johann Radon discovered this new transform which computed integrals along lines, and today these transforms are in fact the basis for CT scans and other reconstruction techniques in tomography. So the Radon transform function computes the Radon transform function. So basically a function of two variables, and you compute an integral along a line given by p and phi, and then you can recover the original function by just doing the inverse Radon transform. Now that's a hard computation, this inverse Radon transform. So basically what happens is that we reduce the inverse Radon transform to a Fourier transform. The Fourier transform reduces to a Hunkel transform, and the Hunkel transform reduces to a Mellin transform. So this computation over here really is relying on lots of other developments in the system. So Radon transforms are in a way the showpiece of integral transforms in version 12. And of course, they are so practical and important. CT scans, of course, are a critical tool for diagnosis these days. And I'm very happy to show this piece of mathematical functionality which underlies this important piece of technology. Okay, now the question that we had before us was, how do we make our documentation even more useful? So we had several interns who are engineering students over here who helped us to work through a very popular textbook by Stewart. We solved all the examples in this book, around 5,000 or more, and based on those improvements and others, we actually have nice new documentation with limit, d, and integrate in this new release. So this, to me, is a nice way for students to learn Mathematica, to learn limits, d, etc., and still progress well in their courses. On the other hand, we have lots of special functions. So we have some talented people over here, physicists and mathematicians, who helped us to make examples for 250 of them, not just 5 or 10, starting from sine and cosine, all the way up to hypergeometrics and elliptic functions. So that's a very nice word cloud which shows you what's improved. And if you now look at the scope section for any of these ref pages, you'll see that they're the same uniform structure. You can learn about numerical evaluation, visualization, differentiation. You can see some nice plots. You can do series expansions, Laplace transforms, etc. And so what you have is a kind of a catalog of properties which work well for each function. So that's a long-term project for us to try and make the special functions easier to learn and apply in the Wolfram language. But to me, the real breakthrough came when some time ago we decided to do a calculus course, a full calculus course. And what we've done now is to actually have a course called Introduction to Calculus, which is an AP Calculus AB equivalent course. So it covers all the topics in that very popular course. And it's got video lessons, problem sessions, exercise, quizzes, and even a sample exam. So you can go to this course and learn whatever you think you need to learn for calculus. And if you do it all well, it's not too difficult, then you can actually get a nice certificate at the end of it, all for free. So I think that really we are a knowledge company, but we are also an education company. And in fact, Stephen Wolfram was here at a picnic last week, and he mentioned to me that every Sunday he teaches programming to middle schoolers. And I think that's the spirit in which we operate. We want to teach, we would like to help people to learn. And today's younger generation is picking up things at a fast pace in the online world. And this course over here really represents our attempt to come to an understanding of how young people learn today. It's been quite popular. We had around 8,000 people visiting the website every month on some estimate. So do encourage anyone whom you know who's young and eager to learn calculus to go to the website and learn calculus for free and give themselves a wonderful certificate. So that's about all that I had to say. And my main point is that calculus in version 12 is now, it's rejuvenated. We are now making things better and better, and you should see more and more things changing as time goes by. But I'm sure by now you really want to see a demo, and that's where my colleague Itai Seggev is an expert. He's worked very hard on this page over here and knows every example really well. So at this point, I'll hand over to Itai, and thank you very much. It's been great speaking with you.
Thank you, Devendra. And let me share my screen. All right. One of my windows disappeared. Hold on. Okay. So I am ready to start the demo, and Devendra can let me know if there are any problems. So I'm going to, try to take you through most of the examples that Devendra didn't show you, but in a more interactive, live fashion. This first example about the behavior of univariate limits is an example I'm actually really excited about. So excited about it, I'm going to start with something that's not part of the example to warm us up. So um, I'm going to take the limit of 1 over x as x goes to 0, and it's going to tell us indeterminate, that the limit doesn't exist. Why it doesn't exist? Well, if we plot it, then we will get minus 1 to 1. Then we'll see that the limit from above is positive infinity, the limit from below is minus infinity. The two one-sided limits are not equal, so the limit doesn't exist. Now, just by way of comparison, I'm going to bring over here a notebook running Mathematica 11, and we'll say limit of 1 over x, x goes to 0, and it tells us positive infinity. So, okay, it took a one-sided limit, and it wanted to take it from above. So if we wanted to take it from below, we'd need to give a direction, which is a number. And as you can see, I can never remember whether it's minus 1 or plus 1, which is from above, and which one is from below. So what happens in version 12? So version 12, as you can see, we get a two-sided limit by default. If we want a one-sided limit, we go x goes to 0, and we say direction. And now we have completions for direction, and you can see that there are two string values from above and from below. So if we want the limit from above, we say limit direction goes to from above. If we want the limit from below, we say from below, and voila. You saw a couple of other directions there. There was reals, which is, that means a two-sided limit in both real directions. And there's complexes, which means to take the limit in the complex plane. So if you're familiar with the point at infinity, 1 over x, as you take the limit goes to 0, is the point at infinity. So that is, just a little warm up about sort of the new capabilities of limit as compared with earlier versions. So now I'm gonna cheat a little bit and just use click to copy to get us started on the actual example. And so here's this function f. It's wildly oscillatory on one side and 0 on the other side. And I'm going to show you how to type in these nice typeset limits. So to type in this limit operator, you use escape, which is how you type in shortcuts. And we see it's escape LIM for a limit operator. And we'll, wrong key. Use control 4 to get us a subscript. X goes to 0, and we leave there, and we see it's indeterminate. Now, this one is, in fact, even worse than the 1 over x example, because one of the one-sided limits doesn't exist. If we take the limit as x goes to 0 from below, which use control 6 to add a superscript to the 0 and just put in a minus sign like you'd expect, we get 0. But if we do the same thing and we do, actually, let me just take that input and I'll change this minus sign to a plus sign. That then we see the one-sided limit doesn't exist. So we have max limit and min limit, also called lim sup, lim inf, and so on. Sorry, apparently my notebook is a bit too small, so if you let me magnify it, and if that, let me know if this continues to be a problem. So sorry about that. Right, so we have max limit, which is also known as lim sup, and min limit, which is also known as lim inf, and we have special characters for those. So for max limit, it's a capital M, Lim, for the shortcut, and we say x goes to 0 from above of f, and that's 1 because we see this crazy oscillatory behavior. It's always getting close to 1. And for min limit, it's very similar shortcut, only it's a lowercase m rather than a capital M. And we see that the lower limit is -1. And in fact, we did this as a, I did this as a one-directional limit, but if we did a two-sided limit, we'd get the same answers because the max and min limits from the left are 0 because the limit is 0. That means both the max and min limits must be 0 as well. So in this particular case, the one-sided max and min limits were the same as the two-sided. Okay, so all right, and then this next example, this gives us a sort of complicated piecewise function. And here, again, I'll start off with just copying the first couple of inputs to get us started. So we're going to take the limit at 0. And if we take the limit as x goes to 0 from below b of g, of g, then we get minus pi over 6, which is right here. And if we take the limit from above, we get plus pi over 6. So if we take the two-sided limit, we get it doesn't exist because even though the two one-sided limits exist, they are not equal to each other. And these last few examples, maybe I will click to copy them just so you can see them slightly larger. These are sort of new, very oscillatory functions that we couldn't necessarily compute limits of before, but now with our new code we can. So that's a nice advance. All right, second example, multivariate limits. So I'll start off again with click to copy here and enter our function. And so we see here when we want to take a limit in a two-directional limit, we say the list of coordinates goes to the list of coordinate values. So list xy goes to list 0, 0, and it tells us that's -1/2. And so we have a plot, and one of the advantages of a live notebook is that I can rotate this so we can see more clearly. The blue plane is at z equals -1/2. And you can see that as we get close to the origin, we are in fact getting close to that plane from all directions. So this is a function where the limit is infinity, and let me, actually I'm going to tweak this one a bit and say exclusion style goes to none, which, oh, that's interesting. Oh, clipping style is what I meant to say. Right, so basically rather than capping here, we can see the hole in here. And yeah, so we can see it's blowing up at the origin, so the limit is in fact positive infinity. And this example is slightly different because now we have a, ooh, that's interesting. I wonder why it copied like that. There we go. So we have this parameter a. We're going to assume that it's real, but even for assuming it's real, we don't necessarily have a limit for everything. So if a is positive, we get the answer 0. If a is not positive, i.e. it's 0 or negative, then the limit doesn't exist, is what this is telling us. So if we create a plot where here we've set a equal to positive 1, then we can see, yeah, it's getting close to 0 as we approach the origin. But if we set a equal to 0, and again, I'm going to add this clipping style goes to none option so we don't get these horizontal lines here, we can see, yeah, as we get to the origin, in some directions it's going to +1, in other directions it's going to, or plus something, plus 20 something, in the others it's going to minus 20 something, so the limit doesn't exist. Okay, so Devendra already showed you this next example, so I will skip it, and we'll look at the functions from the next example. So we define f like this, and I'm actually going to type this in a slightly different form. So you can see on the web page we use this assuming form. Just FYI, you can also put assumptions directly in limit. So if we say assumptions goes to a greater than 0, and there's a reason why I'm typing these out. So we see a condition was generated, and which is a good thing. We need to know where this example is valid. So if we, but there are different ways of handling these conditions. For example, suppose we only want an answer if we don't need any conditions for validity. Then we can say generate conditions goes to none. And because a condition was necessary, it returned unevaluated here. If we just want an answer and ignore the condition, we can say false. So here it gave us the answer, but without the condition. So we don't actually know. So I don't recommend doing this, but if for some reason you really want this, that's a documented option. And true will sort of generate conditions in basically all cases, and automatic is more or less true. There are certain edge cases where it might not generate an example where true does. So here we did, right, so here when we said a greater than 0 and generate conditions goes to none, it returned unevaluated. But if we instead now say a greater than 1 plus log 2, and generate conditions goes to none, well, we get the answer of minus infinity because no condition was actually necessary for this condition. And just for completeness, so we have what happens for 0, and for greater than 0, but we don't have what happens for 0. There you go. Okay. And yeah, so here's a plot. I will, again, just sort of click and copy it. And so we see these are, here's the critical value, a equals 1 plus log of 2. And we can see this green line is approaching the limit of 1 plus log of 2. But everything else, 0. Oh, did I skip over the, I did this wrong, didn't I? Haha. The critical value is 1 plus log of a equals 1 plus log of 2. And in this case, the answer is minus log of 2. So here is minus log of 2, which is minus 0.0707 dot, dot, dot. And we can see that it's approaching the critical value for more positive values of a, then it goes to minus infinity. For less positive values of a, it goes past the critical value all the way to 0. All right, so that completes our first row studying function limits, and now we're ready to look at let me see how I'm doing on time. I'm doing okay. So here's right. Right. So, well, let me just, sorry. Compute this limit, we get 0 as expected, and we can also do multivariate limits as would be expected. So here we're taking the limit of this sequence in 2 variables as they both go to infinity. There's no direction option because the values are either plus or minus infinity. Now again, this plot is a little bit hard to read. So one of the advantages of a live demo is we can rotate it. And so we can see as we get towards increasing values from each side, then we're approaching the limit value of 1 over e more quickly in one direction than the other. So from here, we're approaching it pretty quickly. Here, it's sort of, we're actually crossing over it, and then we'll be working our way back up for larger values. Okay. Then I will copy this, and actually I need to clear f here, so I will clear f, and then I will define this function f, and now we can plot f. So here are 2 plots of f. One is just the normal plot of a sine function, and the other is a discrete plot where we're just plotting its value on the integers. Now, if we just take the normal limit as x goes to infinity of f of x, then we'll get indeterminate because it's oscillating back and forth. The limit doesn't exist. But we can take the max limit and min limit. So again, we replace the limit character with mlim, and this one with lowercase mlim. And we see the upper limit is 1, the lower limit is -1 because we're oscillating back and forth. However, if we take the discrete limit, and the discrete limits are a little bit, well, we could just type it in, of f of x, x goes to infinity, is square root of 3 over 2. We can also type it in the typeset form. It's a little bit complicated. So for discrete limits, it's escape dlim, and you see it creates this little template for us. So we're going to take x to infinity, and our function is f of x. And we have this little subscripted integers here to tell us that it's a discrete limit rather than a normal limit, and we get square root of 3 over 2. And why is it square root of 3 over 2? Well, it's a constant sequence. We cleverly chose our function so that on the integers, it's constant, and therefore the limit exists. In particular, this means that the max limit and min limit, the discrete max limit and discrete min limit also exist and are equal to the limit, as I can show you by just replacing the limit operator with the max limit or min limit operator in the template. And just again, FYI, we have dmlim and the lowercase mlim to create templates for discrete max and min limits. Okay. So this next example, Devendra already showed you, so I will skip over it. Right, so this, we're going to study limit of sequence of functions. So we have this function, and here let me clear G just to make sure don't run into any definitions. I grabbed the wrong one. Here's our definition of G. It's this polynomial raised to an nth power. So it's still a polynomial, but of ever higher degree. And we're going to take the limit on the interval 0 to 1, and it's 0. Because at any fixed x, as n goes to infinity, then we'll have here a number between 0 and 1 raised to the nth power. It's going to get 0 and 0. Now, if we now we're going to take a slightly different limit, where rather than doing it at a fixed value of x, we're going to change the value of x. So we're creating a new sequence of values, which are the maximum value on the interval. And the maximum value goes to infinity as n goes to infinity. So we can see from this plot what's happening, which is the functions are getting sort of higher but narrower with increasing n. So again, eventually each point will be 0, but the maximum value will be 0 and 0. So this is an example of what's called non-uniform convergence. And this has interesting implications for integrals. So if I'm going to take the limit as n goes to infinity of the integral from the lower limit is from 1 to 0 of this g of n. So first we compute the integral, and then we take the limit as n goes to infinity. We get 1/2. So so the limit of the areas is finite. On the other hand, if we first take a limit and then integrate, so I'm going to have here the integral from 0 to 1 of the limit here. N goes to infinity of our g of nx, and compute that integral dx. We get 0 because we know this limit here is 0. The pointwise limit is 0. The integral of 0 is going to be 0. Whereas here we're computing the area, and the limit of the areas is 1/2. So that's a very interesting example. All right. Next example, limit of recursive functions. So our solve value finds the solves recurrence relations, and it has new understanding of asking for values at infinity. So for example, here we're solving this sequence, and we're asking for the value at infinity, and we get log 2. And I want to emphasize that it really does understand that it needs to take a discrete limit here, because if we just found the general value and then plugged in n equals to infinity, then it will yell at us that it ends up with an indeterminate expression minus 1 to the infinity. So there's a general solution in this case, which is that. And then if we just substitute n goes to infinity into that formula, we end up with an indeterminate expression. Then this is another just sort of cute example. If we have we can think of nested radicals as a recurrence equation to solve. And again, with infinity, it knows how to take the limit and give us an answer. Now, this next example is actually really quite interesting. I'm going to type it in a slightly different form. Because so we're trying to solve the equation cosine of x goes equal to x. So we're going to just iterate and say x of n plus 1 equals cosine of x of n. And we need an initial condition. We used pi over 3 just so we'll be sort of close. I'm going to use 0 just because. And if we find x of infinity and n, and I forgot to close my list right there, and we get this answer. So this is what's called a root object. It gives us a numerical approximation, but it's an exact number that the system understands. So if we do n of percent and ask for, I don't know, 300 digits, then we get 300 digits. And if we wanted 1,000, it could give us 1,000 and so on and so forth. What's really interesting about this example is that we can't give you a simple formula for the intermediate expression. If I took this input and instead of asking for x of infinity, I asked for x of n, it returns unevaluated. There's no simple formula that can be given for this. But if you ask for the limit of it, it knows how to find the limit and give you the exact answer to that limit. Okay. Let me see. Just a tiny bit low on time, but I think I'm still doing okay. So let's go on to nth derivatives. Yeah, so let's ask for, like it says here, the nth derivative of cosine of x. And we get this strange, but if we recall our trig identities, these multiples of n pi over 2 change cosines into sines or minus signs and so forth. So if we do percent of that, table of percent with n going from, and I'll actually do here 0 to 4. Then we see for n equals 0, so no derivative, we get cosine of x, and then we get minus sine, minus cosine, sine, and cosine, just like we'd expect. Now, we can actually use this to compute really high order derivatives. So if, whoops, I didn't want that. If, let's say I wanted to compute, 10 to the 9th, absolute timing, that's, and, doing 10 to the 9th derivatives sequentially, even for something as fast as Mathematica, would take a while. If I want the 200th or 500, 10 to the 500th derivative, you can see it's taking the same amount of time because it knows how to skip directly to the formula for the nth derivative and then just plug in n rather than sequentially computing 10 to the 500th derivatives, which, even if it could do that really, really, really fast, would probably take longer than the age of the universe to complete. Okay, right. So Arctan is another. So that was a relatively simple formula. Actually, let me do one other example before. I'm doing this slightly out of order with respect to the page, but I think it's good. Let's take the nth derivative of x to the k. That's x to the k minus n. So we know that when we get n, and when we take n derivatives of x of the power x to the k, we'll end up with a monomial n order of degree n lower. And then there's this factorial power thing. The factorial power, also called the falling power, means take a k times k minus 1 times k minus 2 until you reach k minus n plus 1. So for example, if we substituted in k goes to 6 and n goes to 2, then we'd get 30x to the fourth because we've taken two derivatives of k to the sixth. We get 6 times 5, and so 30x to the fourth. So Arctan is one that's sort of a little sneaky. So we compute the nth derivative, we get this really big and scary looking formula in terms of hypergeometric PFQ regularized. But again, if we take the table and put in concrete values of n, and I want values in n from 0 to 4, then we get arctan, the familiar derivative of 1 over 1 plus x squared, and then the various rational function derivatives. Right. So I spoke about the fact that we can do higher order derivatives very fast. Also, we can give simpler higher order derivatives than we used to using these formulas. So I am going to this is the last example from this page. I'm going to use column rather than table, so I can add dividers just to give us a slightly, and you'll see why. So here are the formulas in version 12. They're not tiny, but they're sort of manageable. We have sort of 2 terms with polynomials in them. Now, if I take this same input and I'm going to now type this into Mathematica 11, these formulas are a little bit bigger. In fact, they don't even entirely fit on the screen. And this one isn't, I haven't even increased the magnification of this one. This one's still at 100%. If I went with 125%, like I have over here, then, they do not fit on the screen. So simpler formulas. Okay. Let's see. Calculus of n derivatives. Yes, this is we have familiar, just like we sum, product, and chain rules for ordinary derivative. There are similar rules for the nth derivatives, not just the first derivatives. The sum one is pretty similar because derivative commutes with summation, so you just get nth derivatives, the sum of the nth derivatives. If you do product rule, you have a sum where you have binomial coefficients, and you're alternately taking derivatives of each side. So if we did a table of that where we took n from 0 to 4, say, and oh, I forgot it's an inactive, so I need to activate this guy, %190 in this case. And yes, let's make this a table form so we can actually see this. So 0th derivative is f plus g. First derivative is the familiar product rule. Then we have 2 of the cross terms plus g times f prime prime and f times g prime prime. And then it's like expanding more and more powers. And finally, we have generalizations of the chain rule. So instead of multiplication, I'm going to do composition. And now I'm going to, again, do a table here. So it has this scary looking val y thing and an inactive table inside of it. But when we expand it out, we see, well, there's the original function, ordinary chain rule for a single derivative, and then various higher order compositions, which don't necessarily fit on the screen. Maybe if I had used the column, it would, yeah, so there's the 4th order term. Okay, this next example was covered by Devendra. So Post has a formula for computing the inverse of a Laplace transform using the limit of the nth derivative. So there's a formula, and we can use it to compute Laplace transform, which fortunately gives us the same answer as the built-in inverse Laplace transform. And then here's a slightly, whoops, apparently did not copy what I thought I had copied. And so, why, oh, it's closed for some reason. There we go. So here, where we know the true answer is e to the t, and we can compute approximations by just taking higher order derivatives in the formula. And yeah, I guess I have enough time for one last example, which is constants of integration. So this has been a long requested feature. Let me just type some things in. So we want the integral of x squared, and we say generated parameters goes to c, where c is our standard built-in function that represents constants of integration. So we get x cubed over 3 plus c of 1. Why is there a little 1 there? Because there might be more than one parameter, as I will show in a second. Now, you can give any name you want to your parameters. You can call them Bob, and then you get x cubed over 3 times Bob of 1. Or you can use subscript, or whatever it is you want to use to call your generated parameters. Now, going back to this guy, now if I do integrate twice with respect to x, then we get x to the fourth, c of 1, and then we get x c of 2. So this is not the same c of 1, obviously, but we get a linear term plus a constant. Now, something more interesting happens if instead of integrating twice with respect to x, I integrate once with respect to x and once with respect to y. So rather than sort of constants of integration, we have functions of integration. We have c1 of y and c2 of x, because if we differentiate those with respect to x and y, well, the x will kill this term, the derivative with respect to y will kill that term, and we end up with x cubed, or sorry, x squared as we expected. And if we did, say, a couple of y's rather than just one y, then we'll get y time, right? So we'll have a c2 of x, and then a y times an arbitrary function of x. And again, if we plug that in, we get x squared back as we thought. So we've added them in not just in integrate, but also in sum, which has integrates constants of summation. And we can verify that using difference delta, which is the, oops. Or we can, or product, which has, whoops, has, not sure what to call them, but it has coefficients out front for indefinite products. If you take the discrete ratio, you get k squared back. And the Devendra went over sort of the remaining examples. I will just briefly go over, due to the shortage of time, the last example, which is Klein's invariance. So we have new functions for various Weierstrass elliptic functions have lots and lots of different named invariants. I mean, we've had sort of the basic core ones for a very long time, since the 90s at least, possibly since the 80s. But um, new in version 12 is we have dedicated functions to give you certain named constants. So we have the Weierstrass E1 through E3, the Weierstrass etas, and so there's this thing called the Klein invariant. We have a built-in function for it, but you can also, using these new, build it up using Weierstrass invariant G2 and G3, and you can get very pretty um, plots using by doing uh, plots uh, of the Weierstrass elliptic functions in the complex plane. So those are all of the examples. I will pause here and see if there are any questions on the live stream that I need to address, or any additional comments Devendra would like to make. But thank you for your attention.
Thank you, Itai. It was great to have that wonderful live demo, which make things so much more clear for everyone. And it was a pleasure to share these new features with you. I hope you enjoyed them. Do let us know if you have any suggestions for the future. We'll be happy to have suggestions from users, new and old. Thank you.